Tatavarty. I lead the AI for 8451. 8451 is owned by Kroger. We are the data science and AI arm of Kroger. Kroger is the largest grocer in the country with 2,700 stores and about $150 billion in revenue per year. So today I'm going to talk about a couple of things. One is speed. And hopefully by end of this talk, have you saved some money or actually think about a new startup which is based on speed. So why is speed important? I think there are different ways to look at it. From an e-commerce perspective, just by going from shipping from 5 days to 1 day, it's about 20% growth in incremental sales or like 20% reduction in cart abandonment. For TikTok, just for them going from recommendations that run in batch to real-time recommendations that run in less than a second. It was like 1.8 billion users and monthly average users. So Amazon, they've done testing with every 100 milliseconds of delay, there's 1% sales that they lose. So speed is a big deal. And there are two ways to get speed. One is the typical scale out approach. The other one is scale in. Scale out is basically distribute the workload across many servers. Classic systems like Hadoop or Spark or Bigtable, so forth. Your work is distributed across many nodes. The other one is scale in, means you have a faster memory, faster GPU, and you try to build larger machines. So you could also have a hybrid approach, which is kind of a combination of scale out. You take the largest server or a GPU possible and then do a scale out. So it could be a combination of strategies. So scale out, scale in, and hybrid. So if you look the computing trends of in the last 50 years or so, one thing you'll realize is what is thought as a batch process is sooner or later become something real time. So for example, just to sort like 1 billion rows, it used to take like probably few months, in 70s or 80s. But now on a MacBook M4, the latest one, probably does that in less than a second. With GPU acceleration, it's actually less than a second. So what you thought as like, hey, I need like, a Spark or like, huge infrastructure to do the computation over time could be, run on a, commodity desktop. And even if you look at the scale out systems, they are becoming larger and larger. So they're also becoming faster, but what you're seeing is earlier, sorting gigabytes of data was a big deal, then terabytes became a big deal, then petabytes was possible, like Google started a 50 petabyte sort in somewhere around 2015. Now you have machines that actually operate at exabyte or exascale computers, like even NV72, the flagship Blackwell system, as well as some of the El Capitan supercomputers, they can deal with exascale. So the fundamental trade-offs here is like between scale in and scale out is in single node, the compute dominates. So when you go scale out or distributed, the network latencies dominate. So you have to think through, and network latency is 10 to 1,000 times slower than memory access or compute latencies. So you have to think through this, shift between the more nodes you add, you're going to add network latency, and that is going to be the slowest part of the process. And you also cannot make something faster than the most serializable or non-parallelizable portion of the code. So Amdahl's law applies. So what are the technology stack? What are the packages we have for both. In the Spark world, we have Spark SQL, Spark MLlib, streaming, graphics. For accelerated compute stack, you have QDF. How many of you use QDF? One, okay. How many have you used pandas? Okay, everyone uses pandas. QDF is like very similar syntax as pandas, except that it runs 100 to 1,000 times faster. The syntax is exactly same, Python bindings. In fact, there is a extension that makes you Python code leave as it is and uses QDF under the hood for acceleration, and you just like use it's like a switch on. You don't have to change the code, and you get that 100x, 200, or 500x performance. QPy is very similar to NumPy, same syntax, but it uses GPUs under the GPU acceleration under the hood. QGraph, again, graph processing. Polars is a Rust-based package that is actually, again, much faster than Pandas and even Spark in some cases. And it works both on CPU as well as GPU. That's the beauty of Polars, is it is not limited to just GPU. And then you have newer languages like Numba or Mojo, which provide transparent acceleration to your applications. So this is the stack, and now we'll go about look at some few benchmarks and see how will you choose whether I want to stay this side Spark, or whether I want to pick a some sort of accelerated computing to do your job. So first is a billion row sort test. So let's generate like billion rows and try to sort them. This is Spark code. Spark is basically lazy, so you'll have to force it to actually print the output, then only it would sort. So this generating and sorting took like 112 seconds. That's the baseline. It's running on an A100 node, but it's only using CPUs. When you convert this to polars, equivalent code, it's again running on CPU, but it runs about in 15.84 seconds on CPU and 5 seconds in GPU. So it's somewhere between 5x to 15x faster. Same hardware, and the benefit you're getting is Polars is very efficient at doing all that serialization, deserialization. It doesn't have to. The orchestration is much more different and efficient than Spark. Now, if you use QDF, the same code, which took 112 seconds, it probably runs in 0.86 seconds. So you're getting just 100x faster. The syntax is very similar to Panda syntax. So, and 1 billion rows is not a lot of data, to be honest. You can easily fit in one of these GPUs, even desktop GPUs these days. So second test is a needle in the haystack and group by. So in data processing, these are the common tasks, right? Like you would sort the data, you would group by, filter. So similar test in Spark, it's running for like 6.73 seconds. It does a fairly good job, actually. Spark is really good at filtering things because it stores them in memory, and it can do that in memory filters. And aggregation also, it's very efficient. Then we convert this into polar CPU about the same time. Not a much significant, slightly slower, but not much a difference. But when you go to GPU, you get 2x faster in polars. So polars, when it uses GPU, it is also using QDF under the hood. So, but when you use actually QDF, it runs in 0.3 seconds, 15x faster. Even filtering and aggregating is faster. So another test is joins. This is a CPU Spark only test with joining a 1 billion row table with 10 million rows. It takes about 145 seconds. So you just simple join key and equi-join, nothing crazy there. The same code when runs in CPU on Polars, it's 5x faster, 26 seconds. So joins are faster. And when you turn on QDF data frames, it's 200 times faster. So do you really want to use Spark for billions of rows? That's the question. You could ask yourself, if you've been heavily Spark shop, are there portions of your code that could be maybe 3 years, 5 years back were like you needed a distributed cluster or like a database query engine, but does it make sense to still keep it in a cluster? Can you move that into just a single node server? That's the question you should be asking. And I just want to also showcase some of the Polars benchmarks. As you can see, pretty much there's like 5 different queries, including data reading and writing. Polars seems to beat popular frameworks like Spark, Dask, Pandas, uh, DuckDB, and so forth. So definitely um, you could try Polars. Again, Polars with GPU acceleration. Um, it has a huge speed up, and the speed up only increases with your data size. So larger data sets tend to benefit a lot more than the smaller data sets. So closing thoughts, I think through your data volume, right? Like these days, some of these GPUs, like A100, have 80 gigs of memory. They cost less than like $2 an hour. That's like as cheap as it gets. In fact, you might be spending more with a CPU node with 96 cores or something. So things are much cheaper. And you could fit, what could you fit in a one GPU? Entire world's population. If you have IDs for everyone on the earth, that could fit in GPU. It's only 64 GB. Entire Wikipedia's triples as a knowledge graph. That's 10 billion triples, maybe 120 GB. H200, the newer ones has like 140 GB or so memory, so you could all fit it in one GPU. Uh, Entire US households, 143 million, only 5.7 GB. So rethink how much data you have, and just being smart about picking your data types, you could actually benefit the GPU acceleration. So broad guidelines, like, is if you have terabytes of data or long ETL jobs where it's their network bound and not compute bound, probably Spark is a better idea. You still, if you have to process terabytes of data and join them, terabytes or petabytes, Spark is still the right tool to use it. But if you're talking gigabytes or billions of rows, that's now in the realm of a single GPU. Um, Orchestration. Sometimes you want to use Spark for orchestration and resource elasticity. So you kick off a job, it's going to spin up as many workers that are needed, and it's running some business process or so. So you're using pretty much Spark for not for like core processing, but like orchestration. That's okay, and that is fine. Spark has resiliency built inside it, so some job fails, it will recover nicely. You'll get the elasticity, compute elasticity. And if you want to integrate with other technologies, like, okay, I want to connect with uh, Kafka or or Snowflake or something. Okay, Spark is a great tool because it gives you consistent data frames for that. But if you are none of those cases on the left side and you need the performance, consider accelerated computing like GPU acceleration. Definitely for low latency applications, when you're talking milliseconds or microseconds, that's the right framework. And also for simulations or data intensive numerical manipulations, like dense matrix operations or simulations or graph analytics, accelerated computing is probably the preferred. And definitely everyone knows for LLMs, there's no other way to run without hardware acceleration or accelerated computing. All the NLP tasks and all your LLMs definitely need those. And last one is like memory intensive workloads and real-time analytics, like dashboards that you want to do. There are few cases where you actually need both. Uh, the accelerated compute as well as Spark. Then you have this option of something called Spark Rapids that lets you actually take advantage of Spark for data processing or feature engineering or just shuffling the data or orchestration, but use GPU acceleration for doing your core task, like doing the computation. So that's a popular choice. This also has advantage of giving transparent acceleration to Spark. So you just turn on the Spark Rapids GPU options and it just your code runs a bit faster, a lot more faster than before. So that's it. This is a unique use case where you need both, and there are ways to using with Spark Rapids. So finally, I want to leave you with this thought of speed ambition. Just like AI ambition, think through what your speed ambition for your organization is. In the sense as speed could be thought as like basic, I'm just gonna save some cost. Like, my code is running faster, I'm saving compute dollars here or there. That's the lower end of speed efficiency. Query acceleration, ETL acceleration, and so forth. You're getting resource and cost savings. The second level is speed as a capability. You're so fast that your speed has become a capability. Real-time recommenders, right? Like it's a new capability. The fact that YouTube or TikTok or Instagram can recommend the freshest content when you refresh your page, that's a new capability compared to, Netflix is, it used to be batch overnight. I don't know what it is today, but the freshness itself is a capability. Um, the token, the token factories and how fast you can generate tokens is a uh, unique capability that the infra providers boast upon. So the last one is speed as a transformation. So you could actually create new business models just being fast. For example, uh, object detection, right? It's so fast, you're doing it like tens of frames or hundreds of frames per second that now you can use for autonomous driving. Um, so determine where your organization's speed ambition is, and based on that, you could position which capabilities you want to move to GPU acceleration or like hardware acceleration. So that's pretty much. And we're hiring. So if anyone is looking for ML engineers or ML director role, reach out to us or just talk to me after the talk. So thank you. Any questions? Mr. Giri,